Okay, so let's start with the healing moments again. First of all, we will deal with the healing moments associated with grain. So grains are contained in the container ships, and these grains, there are some set of rules that are made in regards to the grains. So means regarding the GZ curve, the area of and the different stability conditions. I will just state those conditions again, then we will do a problem. Now, when grains are put into the container, and because of the grain shift, there is a heel, let us say, of the ship. The rule says that the angle of heel should definitely be less than 12 degrees. So, because of the heel, because of the shift in the grain, means grain is there and due to some reason it shifted, as a result of which there is a G0 G1. G0 G1 means there is a shift in the center of gravity, which as a result of which there is a heel, and the first rule says that the maximum angle of heel due to any amount of grain shift, the maximum amount of grain shift, the maximum amount of heel that is occurring should be, it should not be more than 12 degrees, or it should be less than or equal to 12 degrees. It should not be greater than 12 degrees. Then then the second rule is that in the GZ curve, means when you have the statical stability curve. So, suppose this is your writing arm curve, and suppose you have a heeling arm curve like this. Okay. The rule says that the area between the writing arm curve and the heeling arm curve, which is this area, okay, this area between the writing arm curve and the heeling arm curve up to an angle of 40 degrees or an angle of flooding if it occurs before. Angle of flooding means because of its heeling there is some hole that has come to the water, means that hole is actually on the freeboard, but because of the heeling that hole is now come into the water, as a result of which water is entering. So, that is called as angle of flooding. So, the area between the area in the GZ curve between the writing arm and the heeling arm between the angle of 0 degrees and 40 degrees or the angle of flooding if it occurs before, this area should be it should be at least 0.075 meter radians, or it should be greater than or equal to 0.075 meter radians. So, the area between the curves should be at least 0.075 meter radians, that is the second condition. Then the third condition is that GM, the metacentric height, should not be less than, or it should be greater than or equal to 0.3 meter. So, the GM, the metacentric height, should definitely be greater than 0.03 meters. Okay. So, these three conditions are the rules associated with grains. So, some time back I derived some other rules. So, that is what you have to remember all these rules. Actually, in the later stages, will be after the mid semester, we will be doing explicitly with a lot of rules. So, rules associated with this ship, that ship, under different conditions, the wind, heel, all those kinds of rules. There are a lot of rules associated with that you have to by heart and write as such. But for this mid semester, that is in 2 weeks, this much of rules you have to remember associated with grains, and something else I derived some time back. Those are rules associated with some time back I did something here. Okay, merchant ships, yes. So, vessel should have some satisfactory stability, that is the area under the writing curve should not be less than 0.055 meter radians up to an angle of 30 degrees. So, all those things. So, those rules also you have to remember. So, in case you have such merchant ship conditions, that problem will state what you have to apply, which rules you have to apply. The moment you see grains which are in container ships, some kind of container ships, you use these rules. Okay. The angle of heel, these three rules, all three has to be satisfied. So, all three is satisfied means, so the question will be that is the ship stable or is the ship likely to be certified, something like that. So, or if all the three rules are satisfied, then yes, the ship is stable. And note that even if it is 12 degrees, it passes the test. Okay, even if it is 0.3 meter, it passes the test. Similarly, here 0.075, it passes the test. It's always equal to or greater than, not greater than. So, if it is any of those values, you pass the ship. Then some other things which I didn't explain exactly, that is, in case of ship, in case of such grains, we use G0 G1 is written as lambda 0. It is defined as the volumetric healing moment divided by stowage factor into displacement. So, G0 G1, that is the shift in the center of gravity of the grain, which is the shift in the this is the G0 G1 that is producing your healing for the ship, is equal to lambda 0 is equal to volumetric healing moment. Now, this I didn't explain properly what is stowage factor. Now, I think I said something like a fraction or something. It is not exactly that. I was checking that out. Actually, stowage factor means suppose the density of that grain is what should I say, 1.2 into 10 cube kilogram per meter cube. Okay. Let us suppose that the density of the grain is this 1.2 into 10 cube kilogram per meter cube. Then the stowage factor is defined as 1 by 1.2 into 10 power 3. It becomes meter cube per kilogram. Okay. This is the meaning of stowage factor. It is something like 1 by density. Okay. Okay. So, it will become something like 10 power minus 3 kind of thing, meter cube per kilogram. That is the meaning of stowage factor. So, as you can see here, this will be like displacement is in delta. It is not the volumetric displacement, it is the total displacement of the ship, which is the weight of the ship. So, it will be in mass, it will be in kilograms, displacement will be in kilograms, and stowage factor is in meter cube per kilograms. Okay. So, when you do that, you get something like a volume, okay, meter cube, something which is the dimensions of volume. Therefore, you can look at your expression for G0 G1, which is lambda 0. So, it is a volumetric healing moment divided by a volume. So, that is a arm only, it is a distance. So, it is the volume, that is why it becomes, it is like a something like a center of gravity or G0 G1, that is the shift in the center of gravity, that is what gives you G0 G1. Then lambda 40 means lambda at 40 degrees is defined as 0.8 lambda 0. Okay. This is the second expression. So, this too you have to know. Then let us do a problem, probably this will explain, I think. Okay, now you are told that there is a ship which has a light displacement. So, this is the light displacement of 7304 tons, and you are told that its kg is equal to something 10.09 meters. Now, this is a ship in which grain is added. So, first of all, the moment you see the grain, make sure. So, the question is going to be, will the ship satisfy the IMO criterion? These are all IMO criterion. So, will the ship satisfy the IMO criterion? So, you first of all, of course, you have to remember the rules, then you will see how to do the problem. So, now you are given that the stowage factor is 1.3 meter cube per ton. So, these things you have to change. Okay, it is 1.3 meter cube per ton, you change into kilogram, it will become 1.3 into 10 power minus 3 meter cube per kilogram. So, that do not forget that you have to change that. Now, you are told that about the different compartments, they are saying that all compartments are, now that figure that I showed you applies to all compartments, means all compartments are exactly identical, there is no difference whatever is the ullage, we can directly read the volumetric healing moment from that. Now, this is the way in which the different compartments are filled. First compartment, it's filled fully to full. Okay. Second compartment, it says ullage is 8 meter. Third compartment, it says is full. Fourth compartment is full. Fifth compartment, the ullage is 2 meter. Then it says that below that you are going to add oil, which is 1360 tons and kg equal to 1.67 meter. Below that you are adding a fresh water, not below that, somewhere you are adding fresh water, which has 284 tons and it has a kg of 12.72. Actually, you when you do such a problem, there is one additional thing you might get confused, that is, when you are having the oil and water and oil, you might have to take the free surface effect as well. It becomes very complicated problem. Okay. But in this problem as such, they have not given the, for that oil, they have not given the compartment size and all that. So, if you are not given that, that obviously means you neglect the free surface effect of those fresh water or the oil, because this problem is just for sand, we are not doing the other part. In a complicated situation, totally you really have to consider that. So, in this problem we are not going to consider free surface effect, nothing about the freshwater tank size or anything is given, because otherwise you have to find I for the tank. If you remember, for freshwater, for the free surface effect, you have to get I of the tank, that we cannot, we are not given anything about that. So, we will neglect those things. So, this is the data. So, this, what is this for then? Why is this oil and freshwater given? What do you think it is given for? What does it affect? Kg, exactly. It is just for calculating your final kg of the ship. Okay. So, it is just a measurement for kg and not for the movement of g in the horizontal direction, not for that, just for the vertical movement of g, that is the only thing. So, what you first have to do is, you have to find the net volumetric healing moment, you have to find the net kg and net displacement of the ship, because remember we have to find G0 G1, which is lambda 0. In our definition, lambda 0 is equal to G0 G1 is equal to volumetric healing moment divided by stowage factor into displacement. So, what do you need? You need the volumetric healing moment, you need the displacement, two things. Then that means you have now what, G0 G1, from which you can get okay, you have G0 G1, then if you have, then you need to calculate GM. Okay. To get GM, what do you need? Okay, one more thing, Km is given. Okay, in this Km is given as 11.3 meters, that also I forgot to say. Km is given as 11.3 meters. So, what do you have? What are you supposed to find? Remember, the three rules implies you need to find three things. There are three rules associated with grain. The first is the rule associated with theta, the phi, the angle of heel. That means you need to find the angle of heel. Now, what do you need to find the angle of heel? To find the angle of heel, if you remember, we are going to use the equations associated with the inclining test. You should remember the inclining test. To do the inclining test, you need two things, G0 G1 and you need GM. Okay. There are a lot of formulas we have derived so far in this, and of course, they are all interrelated, but you have to remember them, all those formulas. So, you have G0 G1 and you have GM. So, G0 G1 and GM are required in order to calculate the theta. If you want, I can write the formula itself. This is the formula, R0 it comes like this, where R0 by R1, R0 by RS becomes tan theta, no, I think it is cot theta, cot phi. So, this is the formula. So, if you have to find your phi, this is the expression. Please remember this expression. You will definitely have to use, first of all, the question something to do with the derivation of healing inclining test is sure, because it's a very important thing, inclining test. So that means, of course, you will remember. So that method of derivation and the experiment is to be remembered definitely, and this final expression you just keep it by heart. Gm is equal to cot phi into G0 G1. Okay, this expression is needed for a lot of such problems, and if that, without that, this problem is totally, you cannot, you will get totally stuck. Therefore, what you need to find here is phi. We need two things, G0 G1 and Gm. To get Gm, what do we need? We need Gm is equal to Kg minus Km. This expression is to be remembered, Kg minus Km. That means we need Kg, Km minus Kg, sorry, yeah. So Km minus Kg, this expression is to be remembered. Therefore, Gm, Km is given, that is fixed, okay, that there is nothing to do. Kg of the ship has to be found. This is important. From that you will get Gm. So what have we found? First we need to find phi. There is a rule associated with phi. It says that phi should be less than or equal to 12 degrees. Number 2, it says that Gm should be greater than or equal to some value I gave, 0.3 meters, yes. So from these two are required. Then 3, you have to find the area under the GZ curve, GZ phi curve between the healing moment and that area should be greater than something. So we will go step by step. The first thing is to find the, in one table itself we can do most of it. Okay. So let us say this is the component, then the volume, then stowage factor, then volume, this is the weight, kg, moment, VHM. Now we make a table like this. This table should be able to calculate everything that you need in regards to this problem, that is we need to find the kg and lambda 0. So to do that, this table should be enough. So you have, let us take the first one, component is the light ship. Now light ship, there is no volume or stowage factor, the weight is given 7304 tons and its kg is given 10.09 meters. So you find the moment. Is there any volumetric healing moment associated with the light ship? Note, volumetric healing moment is the healing moment associated with the shift of grain in a compartment. The light ship itself has no volumetric healing moment, there is no grain there. So the light ship has no volumetric healing moment, so this is not there. Then you consider the first compartment in which grain has been added. They are told, now how do you find the volume of the first compartment? This is the first compartment is full. So in this way you complete the table, you do it for all the components, and finally you have, in the end what you have? You have a, they have said oil. So all the different compartments are done, 1, 2, 3, 4, 5. So all the compartments are done, and then you have oil. For oil there is no volumetric healing moment. Volumetric healing moment is defined only for grain. It is a particular property of grain. As you might imagine, oil also shifts like grain, no such thing. It is defined like that. Volumetric healing moment is defined only for grain. Therefore, forget about, there is no volumetric healing moment as far as the grain, as far as the oil is concerned. So this is not there, but this oil is given just for the sake of its weight and kg. Therefore, here only two things are important. Weight, it is given 1360 tons. So this comes, and its kg is given 1.67, and similarly you have fresh water. Fresh water is given, which has it says 284 tons and its kg is 12.12. Okay, now we have the complete table. Now, what do we find out from this table? See, here we have the total moment, which is weight into the kg, that moment, sum of the total moment, sigma moment, and this when summed up will give you the sigma weight, and therefore, your net kg of the ship after all the healing, everything is over, the net kg of the ship will be given by the sigma moment divided by sigma weight. This will give you the net kg of the ship. So, now you have the kg. So, that is solved for. That is a very important thing. One important part is over. Now, you are given your km, it is given, km value is given, and note that these km values are not going to change because of the shift of grain or anything, km is fixed. Therefore, you do km minus kg, you get your gm. And in this particular case, when you do that, you end up with a kg equal to some 7.8, km equal to 11.3, and you end up with gm equal to about 3.5 meters. Okay. So, this is the first thing you have to check. It says that gm should be greater than 0.3 meters, that is the first condition. So, in this case you are getting gm to be 3.5 meters. So, you have no problem as far as that is concerned. So, that is the first check. Now, that is satisfied. Next is okay, next you have to calculate lambda 0. Okay. Now, lambda 0 is given by the formula volumetric healing moment divided by displacement into stowage factor, something like this. Now, now again same thing we do. We'll look at this table. So, you have the total volumetric healing moment as your last component in the table, as your last column in the table. Sum of those volumetric healing moments, you will get the sigma volumetric healing moment, that is your total volumetric healing moment. So, here this is what it is, lambda 0 is equal to sigma volumetric healing moment divided by displacement into stowage factor. So, sigma volumetric healing moment I told you that is the last column, then sigma displacement is this sigma weight. Okay. So, you have sigma volumetric healing moment divided by sigma weight into stowage factor. Stowage factor is a constant, some 1.3 meter cube per ton, that is given. So, this gives you lambda 0. Now, this is equal to G0 G1. Now, note that you have already have Gm. Therefore, Gm is equal to cot phi into G0 G1. Use that formula and find phi. Okay. And if you have phi, in this case you will get phi to be 6.2 degrees. It should be less, what did we say? It should be less than 12 degrees or should be less than 12 degrees. So, that is also satisfied. So, 6.2 degrees, it satisfies that it should be less than 12 degrees. That is the second criterion. So, two criterions are satisfied. Now, the third thing is to find your GZ, the area under the GZ curve. Now, to do that you have to be given the GZ curve, otherwise you cannot do that. Okay. So, that will be given, and either a GZ curve or a GZ table will be given to you. So, the rest becomes very simple, that is means you are given your GZ table, as you just draw the curve. So, you are given your GZ curve. Now, how do you draw the healing moment? The healing moment is drawn like this. Remember, you have drawn lambda 0, right? Here somewhere around this point you mark lambda 0, you have measured lambda 0, I mean not measured, calculated lambda 0 as here. Here you have calculated lambda 0 as sigma volumetric healing moment divided by displacement into stowage factor. Okay, this is something like a healing arm. Okay, lambda 0 is like a healing arm. Therefore, this lambda 0 is showing your healing arm. Now, lambda 0, the healing arm slowly changes when when the ship heals, that healing moment changes, and because of which, so the method is adopted is lambda 0 is marked here, then 0.8 lambda 0 isn't it 0.8 lambda. Now, 0.8 lambda 0 is marked here at 40 degrees. Let us assume this is 40 degrees, this is 0 degrees. At 0 degrees lambda 0 is marked. At 40 degrees you mark 0.8 lambda 0, okay, and draw a straight line through these two. This will give you the healing arm. So, this is your healing arm curve, and therefore, your objective now becomes to find the area under the area between the healing arm and the writing arm curve, which is this, between 0 and 40 degrees. So, between 0 and 40 degrees, this is the angle between the healing arm and the no, actually this is also an area, no, under the curve. So, this is the total area between the healing arm and the writing arm curve. Okay. So, this total area is what you have to find out, and so this area should be, I think it should be greater than point something 0.075 meter radians. So, in this problem you will have, how do you find the area under the GZ? And first of all, okay, so you need to find, so this is how you find the area under the curve. You have the heel angle, then you have your GZ, then you will have your Simpson's multiplier, then function of area. So, heel of 10, 20, 30, 40. So, this, and so you have your different GZs, you read from the graph, okay, or you will be given the GZ table from which you write these values, and Simpson's multiplier is put here 1424, you put that Simpson's multiplier or trapezoidal multiplier, you put that here, you find the area. Okay. So, you find the area up to 40 degrees, then note, when you find the area under the GZ curve, you are actually finding this area, you will be finding the area under the writing arm curve. Then you need to find the area under this trapezium, you need to find this area of the trapezium made by lambda 0 and 0.8 lambda 0, and you have to subtract that. Okay. So, that will give you the area under the area between the writing arm and the healing arm curve. Okay.
So, why up to 40 degrees chosen?
That is a good question. I do not remember right now. Let me think. What is the importance of 40 degrees you are saying, no? 40 degrees, I have to check that. I remember something, but I can't recall it now. So, that is why they have chosen 40 degrees as the limit at which this area is. So, it is always taken as 40 degrees. There is some reason for that, I will tell you. Then actually, I think if you look at the equation for, I think it is because at now, one of the rules always in the ship design is that the GZ curve, the maximum should always occur less than 40 degrees or 35 degrees or something, that is a rule. Okay. that maximum should always be less than 30 degree. So, beyond that value, if you take some, it's not an exact thing, it means the rule is not defined such that it's, we will see in the next, we have given always some safety factor to it, and then we are calculating the rule, we are making the rule. So, from 30 they have given, so that means the GZ curve maximum will never be greater than 40 degrees. It has to do something to do with that. I will check that. So, this is the why the area should be less than 0.075 meter radians. So, you find this area between the two curves. In this case, you will get it something some 0.524 radians, okay, meter radians, okay. And let me check this, I think I didn't explain it properly, something I missed here, wait. The residual area between the healing arm curve and the writing arm curve up to the angle of maximum difference or the angle of flooding should not be less than 0.075 meter radians. Actually, that's one myth, that is what they have done is, see where the what is this point? This will be the point where the healing arm curve equals the writing arm curve, okay. This will be, in this case we have got it as 6.2 degrees, this is how we have defined it. So, the area from that curve, from that angle, so the area from that angle up to 40 degrees should be less than should be greater than 0.075 meter radians is the rule. So, this area should not be taken. So, you have to take the area from 6.2 degrees to 40 degrees, okay. It is not the whole area, that is the rule. This area. So, first you have to find the area between the, first you have to find the area of the GZ curve between 6.2 degrees and 40 degrees, that will give you this whole area, this area plus this area. Subtract the area of this trapezium from it, and therefore, you will get the area between 6.2 degrees and 40 degrees. So, that area should be greater than 0.075 meter radians. In this case, it comes to 0.524 meter radians, and therefore, this is much greater than 0.075 meter radians. Therefore, you have it's okay. So, it is satisfying all the, so till now we have three conditions, all three conditions are satisfied by this ship. Okay. So, I will repeat this because it is very important, and I told this wrongly, that is, first GM should be greater than 0.3 meter radians, greater than or equal to 0.3 meter, okay. So, that is the first condition, that is okay. Number 2 is the angle of heel, maximum angle of heel. How will you get the maximum angle of heel? You will get it from the equation for healing, equation for the inclining test. GM is equal to cot phi into G0 G1. GM you have, G0 G1 is got using volumetric healing moment divided by stowage factor into displacement, that formula. You, from that you will get G0 G1. With that you get the value of cot phi, that is phi, you get the value of phi. Once you have phi, you make sure the value of phi is less than or equal to 12 degrees, that is your second condition of stability. Then the angle between this value, that is this phi, in this case 6.2 degrees, this phi and 40 degrees, it is not between 0 and 40 degrees, it is the area between this angle and 40 degrees should be less than or equal to, should be greater than or equal to 0.075 meter radians, that is the third rule. So, couple of things that you will, so just to clarify, a couple of formulas that you definitely have to be able to do is, first thing is, of course, you have to be able, once given the first given the GZ table or the GZ curve, you should be able to find the area under the GZ curve. You should know how to do that. It's very simple. You are just going to Simpsonize the thing and you get the area under the GZ curve. So that you should be able to do. That is the first thing. Second thing, remember this expression of the inclining test. GM is equal to cot phi into G0 G1. This definitely has to be remembered. If you do not remember this, you cannot do anything. So once you have that, you have to get phi. Note that, okay, actually, and then the third thing is, what is the third thing? You have to be able to find G0 G1, okay, and 4 is to actually we should be going in this direction, back up 4. So first we find the Kg, then you have Km given. So Km minus Kg will give you Gm. So you have the Gm. Then you find G0 G1 using the volumetric healing moment, which is lambda 0. Once you have G0 G1 and Gm, you can get phi, that you are going to step 2. The Gm and G0 G1 are there, you get phi. From this you go to find, so from that phi up to 40 degrees you find the area. So you go like this, 4, 3, 2, 1, like that you go up and the problem is solved, okay. And then all the 3 criterions should be checked, and so in this, to do one problem like this, I think will take 1 hour, probably 45 minutes at least to do the whole problem. So I might not give you a problem as such, because that is too difficult, but I will ask you the steps to solve the problem, that you can write in 15 minutes, okay. That's what these steps you should write. Suppose I will give you, suppose that if such a problem is given, you, how do you solve it? So that you should be able to do. Okay. Actually, the next one, it's very long. I don't think we will be able to finish this in this class, but we will start with it. Now it is due to the wind. Now we are going to find, right now we found the healing due to grain, okay. Next is the healing due to wind. So our purpose is now to find the healing due to wind. Now the way in which we define the problem is like this. Suppose you have the ship here, part of the ship below the draft is under the water, part of the ship above the ship is part of the ship above the water is known as, let's call it the it's the freeboard, it's called windage area, means this is the amount of area that is open to the wind. So this area, this is the ship, okay, this is the longitudinal direction of the ship, and at this point we have the water line. So this much is below the water and this much is above the water. So this area is the windage area, this plus this plus this plus this, that is the total windage area. Now the way in which we define this problem is like this. So the wind acts, let's say wind acts like this, causing the ship to heel here, okay. So what we assume is that wind provides some force to the ship, okay. That force acts on the centroid of the windage area, means the distance between the draft to the top of the ship, the topmost point of the ship, the half of that distance we will call it as a centroid of the windage area. There the force due to the wind acts. This force tends to actually push the ship like this. Water here will prevent the ship from moving. Therefore, water will provide a reaction force from the Now we assume that reaction force to act at the centroid of the water region under the water, that means at draft by 2. So whatever is draft by 2, at that point the reaction from the water will act, which is equal to the wind force. Why do we say that? We assume that because if the ship is like this, when the wind acts, we assume that the ship does not move like this at any way, it remains there only. So this force is equal to this force, okay. this force acts at the centroid of this windage area, this force from the water acts at the centroid of the water, that is logical assumption only, this acts here, this acts here. So, there is a force acting here, there is a force acting here, as you can see there is a moment produced, okay. One force like this, one force like this, and this moment tends to heel the ship like this, and it comes from logic. Now, when the wind acts, the ship should heel like this, but from a pure force, balance, moment kind of view, this is how it acts. There is a force, there is a force, this different, this force, this distance into that force, that will cause a moment. So, what exactly is the distance between the forces here? It will be the top, that is what, the top of the ship, top of the superstructure. Even if you really want to make the problem more complicated, you will see that superstructure does not really extend whole of the ship. So, windage area becomes a slightly difficult thing, to find the centroid becomes slightly more difficult. It is the actual centroid, it does not matter where, it means this distance, the vertical distance, you find the centroid. So, roughly we can say top of the superstructure, the distance between the top of the superstructure to the water line, half of that distance, okay. Half of that distance will be the centroid of the windage area. So, there one force, here one force, the distance between the forces, therefore, you can see that so the distance between the forces becomes something like, if T is the draft, T by 2 plus L, where L is the centroid, L is the distance between the water line to the centroid of the windage area. Distance between water line, distance between the water line to the centroid of the windage area. Okay. So, this is roughly like your heeling moment, this is what is causing your heeling moment, heeling. So, this is your heeling moment. Now, how do we solve the problem? Okay. When you are designing a ship, note that you will not be knowing what is the wind acting on it. So, obviously, the first step is to assume the worst possible wind and design it like that. So, that is what they do. So, during the design stages, what they do is you assume that the windage area is subjected to a steady wind loading of 48.5 kilogram per meter squared. So, 48.5 kilogram per meter square of this is the maximum kind of wind which can come anywhere. That is why its wind force, this is the maximum you can get. Very, I do not think it is not even the maximum, it is maximum plus some safety factor. Okay. So, it is the that is the limit. So, so assume that 48.5 kilogram per meter square of wind is acting, and as a result, when multiplied with the windage area will in turn will depend upon the ship. Okay. The windage area depends on the ship, it is the area of the ship, but this 48.5 is the maximum wind loading per windage area. So, multiplied with the windage area, you will get the force. Okay. So, 48.5 multiplied with the area will give you the force. So, this is the total force due to the wind. Same is the force acting as a reaction from the water, because the ship as such is not moving horizontally, means the ship is only heeling. Therefore, this force is equal to this force, and that is given by 48.5. This is the force acting. Now, therefore, what is the heeling moment? Let us call this F. Heeling moment will be F into T by 2 plus L. Okay. This will be your heeling moment. Now, we have a set of rules which tell you how you have to solve for this wind case. This is a long process, it probably will take one class in itself. Probably will stop here. I think there is a so this is how you start with the wind, and now there are a set of assumptions. Basically, this is how you check if the stability is satisfied. you have to follow a series, it is like a what is it, an algorithm, that series of steps you have to follow, which and then you decide whether the ship is stable or not. We will do that in the next class. Okay, we will stop here. Thank you.